Expanding on our previous lessons, our Lesson 99 homework was to create a program that would sweep one servo motor between 0 degrees and 180 degrees and back again, while a second servo motor was sweeping from 180 degrees to 0 degrees and back. In this assignment, we were expected to use micropython code to calculate the servo control pulse widths, but the actual servo control signal was to be generated with state machine assembler code such as that developed in Lesson 97. There's a link to the Lesson 97 homework in the description below this video. Each servo motor requires its own control signal. The Lesson 97 assembler code can only generate one pulse width, but there's no need to struggle over creating new code that will manage two control signals. We should be able to install a second copy of our working code in a second state machine. Each copy of the code will manage its own control signal. But will two copies of the assembler code fit into the Pico? As it turns out, they will. The Pico W has two PIO blocks as shown here. Each PIO block contains 4 state machines, each with an independent set of registers, FIFO, OSR, etc. Each of the 4 state machines can contain its own assembler code. However, the length of the code in each state machine is limited to 32 so-called active instructions. Active instructions do not include label and wrap or wrap target instructions. Also, the combined length of all the unique code segments in a PIO block cannot exceed 32 active instructions. Unique is the key word here. It seems that providing that a code segment satisfies the 32-line limit for its own state machine, installing that code in multiple state machines does not add to the combined total. Finally, the amount of code in one PIO block has no impact on the amount of code that can be loaded into the other PIO. The question is, how to prove all this? I started with the working assembler code for this assignment. Discounting the label statements, the code is 10 active instructions in length. This one piece of code installed in both SM0 and SM1 with no errors. I added 22 no-op instructions to the code, increasing the line count to 32. That's a total of 64 lines of code loaded into SM0 and SM1. Even so, it did not violate the combined length less than or equal to 32 lines rule because both sets of code are identical. Just to be complete, I added one more no-op, which brought the code length to 33. As you would expect, this caused the error shown here. Here's the full assignment code. As usual, we start with imports. We import pin because we use the pin statement in the PIO instantiations. We import RP2 because we're going to be programming state machines. We also import time. More about that later. The RP2 decorator on line 5 specifies that we'll be using set instead of out. We'll start with our output pin low, and we're setting the shift direction parameter to right. Because the set servo position function definition follows the RP2 decorator, it will be interpreted as assembler code, not micropython code. The set servo position function has not changed since lesson 98. It starts by moving null into the ISR and OSR to clear out any previous data. The remainder of the assembler code is the decrementing counter from lesson 97, which creates our servo control pulse. The Python program uses a straight line conversion to calculate the pulse width of the control pulse for each required servo angle. This section of the program determines the slope and y-intercept for that conversion equation. Line 30 declares the required period for both of our servo control signals in microseconds. Line 32 instantiates state machine 0 by specifying the state machine number, the name of the function containing the assembler code, and the operating frequency. It also specifies the least significant GPIO output pin, i.e. the pin for servo number 1. Line 33 activates state machine 0. Line 34 puts the period spec into the transmit FIFO of state machine 0. Line 35 executes the pull command as if it was running in state machine 0. This command pulls the period spec from TX FIFO into the OSR of state machine 0. And the exec command on line 36 moves the period spec from the OSR of state machine 0 into the ISR in state machine 0. There's more to be said about line 37 later. The code from line 38 to 42 sets up state machine 1 in a similar way to state machine 0, instantiating the state machine, activating it, then loading the period spec into the ISR. Notice that the set base setting points to pin 7 for SM1 rather than the pin 0 reference for SM0. This is because we're connecting the second servo motor to pin 7. The remainder of the program is a try except clause containing a while true loop and a control C exception. The while true loop contains two for loops, one that counts up from 0 degrees to 180 degrees and a second that counts down from 180 degrees to 0 degrees. Each for loop calculates a unique servo control pulse width for each state machine, one being 180 degrees apart from the other. These pulse width variables are then put into the appropriate TX FIFO and pulled into the OSR. The timing of the state machine program is not significantly affected by these exec statements. Each program simply uses the current pulse width whenever execution loops back to the start counting label. The control C exception will deactivate the state machines and message the user that the program has stopped. And here's how it works. Here we can see two control signals, SM0 shown in yellow and SM1 shown in magenta. As you can see, each control signal has a period of 20,000 microseconds. We can see the pulse widths of the two servo control signals sweeping between 500 microseconds and 2,500 microseconds as required. The pulse widths are also out of phase, one increasing as the other decreases. So individually, the signals are fine. What caught me by surprise was how the two signals were unsynchronized. It looks like SM1 changes marginally before SM0. This isn't a problem in this assignment, but I can see it being a problem in an application where the two motors have to move in lockstep, perhaps an XY table or a robotic application. I had not anticipated this situation, so I decided that I should understand it better. Considering that both state machines are running the same assembler code at the same speed, and SM1 is activated after SM0, it's hard to imagine how SM1 could get ahead of SM0. I used time.ticks milliseconds to determine that approximately 33 milliseconds elapses between the activations on line 33 and line 39. So SM1 actually starts late and runs consistently 33 milliseconds behind SM0. If we change our oscilloscope reference point, we can verify that SM1 is 33 milliseconds behind SM0. The assembler code cycle time is 20 milliseconds, and we now know that SM1 is already starting 33 milliseconds late. By delaying the activation of SM1 an additional 7 milliseconds with the time.sleep command on line 37, we can bring the total delay to 40 milliseconds, which is a multiple of 20 milliseconds, and this brings the two signals into sync. That's all well and good, but there must be a better solution than making an existing delay worse until you get the effect you want. A better solution might be to change the state machine programs so that after activation, they would wait for a single go signal from micropython. Sounds like a job for state machine interrupts. A new IRQ block 0 statement inserted at line 10 sets IRQ 0 and forces the state machine to wait for IRQ 0 to be cleared before proceeding. Regardless of the delay between their activation times, both state machines will stall at line 10, waiting for IRQ 0 to be cleared. In other words, they'll be in sync. Stalled, but in sync. When the micropython program executes the new statement on line 43, IRQ0 will be cleared, and SM0 and SM1 will resume together, still in sync. If we expand the oscilloscope trace, we can see that SM0 and SM1 are within 0.05 milliseconds of each other. And here's how it looks. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.